In this tutorial, we will be discussing different types of solids. Let's start with atomic solids. Noble gases in solid form are classified as atomic solids. They are held together by weak dispersion forces, which then create very low melting points. They tend to arrange themselves in the closest packed structures, such as hexagonal closest packed or cubic closest packed. This maximizes the attractive forces and minimizes the energy. With metallic atomic substances, they are held together by metallic bonds, and these strengths vary depending on the size and the charges of the cations, and they create coulombic attractions, meaning the positive and negative interactions. Their melting point then varies depending on what substance it is. They're mostly closest packed arrangements of the lattice points. And on those lattice points are the cations. Metal atoms release their valence electrons, which you may remember as the outermost electrons, with the metal cations being fixed as islands. So the cations are sitting on the lattice points, where the sea of electrons is derived by the valence electrons, the outermost electrons that have been released, and they are able to flow between the cations. Here's a couple of examples, with nickel being cubic closest packed and zinc being hexagonal closest packed. Now, network covalent solids tend to be stronger. Atoms are attached to the nearest neighbor by covalent bonds. Due to the directionality of the covalent bonds, these solids do not tend to form closest packed arrangements in the crystal. The strength of the covalent bond within the solids is why they tend to have very high melting points, generally over 1,000 degrees Celsius. The physical properties of network covalent solids are related to the dimensionality of the network. In other words, how many directions that the bonds are created. Let's take a comparison of the diamond versus the graphite you would have in a pencil. The carbon atoms in a diamond have 4 covalent bonds surrounding the atoms, forming an sp3 arrangement in a tetrahedral geometry. This arrangement effectively makes each crystal one giant molecule held together by covalent bonds. This explains why diamond is one of the hardest naturally occurring materials found on Earth. So if we look at the diamond arrangement, let's take this atom here, for instance, this carbon. It's formed in 4 different directions to 4 other carbons. And then this carbon that it's bonded to also has 4 carbons bonded to it if you include the original one. And then this one then has 4 more. So this multi-dimensional arrangement is making it extremely strong. Let's look at the graphite. The carbon atoms are in a sheet which are covalently bonded together, forming a 6-membered flat ring fused together, similar to a benzene. So here's a 6-membered flat ring, like a hexagon. The bond length is approximately 142 picometers, with an sp2 arrangement. Each carbon has 3 sigma bonds and 1 pi bond, and it has a trigonal planar geometry. Each sheet is considered one giant molecule, so one hexagon bonded to another hexagon. The sheets are then stacked and held together by dispersion forces, which, as you may remember, are the weakest of the intermolecular forces. Sheets are 341 picometers apart, so the bond length is 142. The sheets are over twice the distance between them. So here we have the graphite. You might very vaguely be able to see, maybe kind of difficult, that there's little hexagons embedded there. And the hexagons are then fused together. and then these sheets are then held together by dispersion forces, which just makes it crumble. So, compare and contrast. Diamonds are multi-directional bonding, while graphites are hexagonal sheets. They both have very high melting points because they both need to break those covalent bonds. However, diamonds, because they're in all three directions, are very rigid and very hard. They're used as abrasive sometimes. Whereas graphite feels slippery because there are only dispersion forces holding the sheets together. They can slip past each other and they glide on the planes, and they're used a lot of times as lubricants. Diamonds are electrical insulators, while graphites are considered conductors. And finally, they're both chemically non-reactive because they're very strong bonds. Silicates are found in approximately 90% of the Earth's surface. Their solids tend to extend an array of silicon and oxygen bonded together. Sometimes aluminum is substituted for that silicon. Glass and quartz, or sand, are types of silicate compounds. Glass is an amorphous form, while quartz is very clear where some impurities are added, which are crystalline. Three-dimensional array of silicon covalently bonded to 4 oxygen is how you'll find these molecules. Quartz is a tetrahedral arrangement. The properties of approximately 1600 degrees Celsius, and they're very hard. So here's a picture of it. With glass is an amorphous solid with very random arrangement, whereas a quartz is a crystalline solid that is very structured.